Welcome to Study Loop.
So this problem has us looking at the gravitational force between a small point mass of little m and then a solid disk of mass, capital M, that's uniformly dense. So the problem suggests that we tackle this by breaking this disk into infinitely thin rings. So that seems like a good approach, so we'll do that. So that means this disk, we're going to say, is composed of infinitely thin rings, and so each of these rings will have a circumference of 2 pi r, where r is the radius of a given ring out to the maximum value of a, and then they'll have a width of dr. So that means then the differential area for each of these disks would just be 2 pi r dr, each of these rings rather. So we're going to want to find the differential mass next, and then we'll substitute that into our force equation, and that will allow us to then integrate that and find what the total force will be. So our differential mass should just be this differential area times the density of the disk. And so this is just the 2D density, so we usually write that as a sigma. And this two-dimensional density should just be the total mass of the disk divided by its surface area, since we're kind of assuming it's infinitely thin then in the vertical direction there. So that'll just be pi a squared. And so then we can plug in our dA that we found. And so we can say that our differential ring mass element here is going to be m over pi a squared times 2 pi r dr. So now we can set up what our force of gravity will be here. So that will be the integral of g, and then the little mass, and then our dm term. So m over pi a squared times 2 pi r dr. And then we want this divided by the separation distance squared. So normally we write that as r, but we've been using r as the radius of our rings here. So I'll write this as a cursive r. So that is the distance from a given ring out to this mass. So that is r. So we can simplify a little bit. We can get rid of those pi's, and we'll substitute in for this cursive r right away. So any points here, we can make this into a right triangle, and so it's the hypotenuse of a right triangle that has one side of x and the other side of our variable regular little r. So this should become gm and then the square root of x squared plus little r squared, and then that whole thing squared. And then we have mass over a squared and then r dr. And I think we still have a 2 here. So we can bring out some of these constants. So we'll have 2 times g little m big M over a squared, and we're just left with our integral of r dr. And then this square gets rid of the square root, so just over x squared plus r squared. And originally this was just over the whole mass of the disk, but then when we change things to r, now we're going from 0 to a. So from rings that have no circumference all the way out to now our rings that are the full circumference of the disk. So from 0 to a. And so at this point, you can do this integral using a u substitution. More realistically, you might look this up in a table or use your preferred method of solving somewhat hard integrals. And so when you do that, you should get our constant still. And then this will evaluate to 1 minus x over square root of x squared plus a squared. So that is our force. And this will be in just straight in the downward direction for the force being applied on the little mass. So just straight down. So by symmetry, there's going to be no force in the horizontal direction. Lastly, they ask us to check this expression and show that when x is much larger than a, that this reduces to the expected form. So the expected form usually just being if we treated both of these as point masses with some separation x. So this term in here with the x over square root of x squared plus a squared, if we do a binomial expansion on that, we'll just go on the next page for that. So we have our force is 2g little m big M over a squared. And then we had 1 minus, and so now if we do a binomial expansion on this second term here, we'll get that that is equal to 1/2 of a over x squared. That is a 1 minus 1/2. So a lot of parentheses in there. So these ones are going to go away, and we'd be left with just a plus this 1/2 term. So we have 2gmm over a squared, then multiplied by 1/2 a squared over x squared. And so now we finally have some things canceling. This a squared goes away, these 2's go away, and we're just left with g little m big M over x squared. So exactly then the force we'd expect between 2 point particles of mass little m and big M separated by a distance of x squared.